Namaste dear learners. Today we are going to see an emerging and excellent concept in semiconductors, that is LED, means light emitting diode, which we see regularly in our homes, offices, colleges, anywhere. In this video I am going to explain about the LED's introduction, electronic symbol, principle, construction of LED, working of LED, and output wavelength in from LED, and VI characteristics, along with advantages, disadvantages, and applications. And light emitting diode, we know in simple we call it as LED, was invented by Nick Holnick Jr. in the year 1962, and the color of that LED is red. When voltage is applied across the PN junction, resulting in diode current, which in turn can produce a photons and a light output. This mechanism is only called injection electroluminescence. So that device is only known as light emitting diode. In simple, you can say which converts an electrical energy to light energy. The electronic symbol of LED is this one. If you observe carefully, this one is a normal diode and these arrows represent emission of light. So a diode which is emitting light is only what our LED. Now we will see the principle in LED. PN junction emits a light when electrical energy is applied to it. This phenomena is generally called electroluminescence. But what is electroluminescence? When p-n junction is forward biased, then electrons cross from n region and recombine with the holes in p region and emits energy in the form of light. And this, when at this time the diode should be under the influence of electric field. And here this p-type emits a holes towards the junction and electrons towards the junction. Here the recombination takes place and photon gets released. This phenomena is only called electroluminescence. So to do this process, only direct bandgap semiconductors are used to fabricate these LEDs. What are direct bandgap semiconductors? Already we had discussed in our one of the previous videos. So you can refer that. Now come to the construction of LED. A typical construction of LED is shown here, so which consists of a reflective coating with on this substrate of N-type and P-type, and here the main important thing, this junction should be near to the outway or exit. So LED is constructed on N-doped substrate, generally gallium phosphate. Why gallium phosphate? In simple, it is a direct bandgap semiconductor. A thin epitaxial p-doped GAP layer is grown on the top of this substrate, and electrical contacts here are made, leaving as much of upper surface of a p material uncovered. The recombination takes place and radiation is between the p and n layers, that is p-n junction, which I marked in red in this diagram. Since GAP layer is a transparent, the radiation escapes from the top layer as shown here. The bottom electrode is a reflective layer and is added to improve the efficiency. Means the photons coming in this direction will hit here and reflect, and coming out from the exit, the intensity of an exit can be enhanced by using this reflective coating. Now LED has been designed and constructed in such a way that most of the radiative recombinations takes place from the side of a junction nearest to the surface, so that loss due to absorption will be minimized, which will improve the output intensity of LED. For this, p-n junction layer has to be parallel and closer to the surface layer. Now, see the working of it. LED works very much similar to our normal diode under forward bias. Here, same as this P-type and N-type connected under forward bias. Now, when we connect this under forward bias, N-type semiconductor here is heavily doped than P-type, forming the PN junction. The potential barrier gets reduced when you connect under forward bias, and electrons and holes gets combined at the junction or depletion region. And here we only call this region as an active region also. Light or photons are emitted in all the directions here, but due to reflective electrodes, photons are directed in a single direction as we discussed in the previous slide. Now, the thing is, the photons are released, but what is the wavelength of that photons? Or what is the color of that LED? We know the basic equation E is equal to h nu. Here, in this semiconductor or LED, E refers to the energy gap. In simple, that is EC and EV, or we can say it is the difference between lowest energy of the conduction band to the highest energy of the valency band. So EC minus EV can be written as h nu, and we know all nu can be written as C by lambda, and this refers to the energy gap. Now by replacing those terms, we can write Eg is equal to hc by lambda, or I can rewrite it as lambda is equal to hc by Eg. So lambda is purely depends on the energy gap of a semiconductor. Now we'll see the Vi characteristics when PN junction is connected under forward bias. For small amount of voltage, electrons in N region, holes in P region cannot cross the depletion region. When voltage is increased to certain value, the electrons in N region and holes in P region cross the depletion region and recombine. Recombinations will start. As a result, photons gets released. From that point onwards, as we increase the voltage, then more and more the recombinations takes place more and more photons will be released, and the voltage where the current start across the junction, or the voltage where the recombination of electron and hole takes place, is called cutoff voltage. Now we'll see the graph of this Vi characteristics. For this, we have taken voltage on x-axis, current on y-axis. Now for small voltages, there is no current flow across the junction, no photons. So this one is 0. From this point onwards, current starts increasing with the voltage. Now this voltage is only taken as cutoff voltage. Now the advantages of LEDs. It's very low voltage and current are enough to drive LED. Because of this advantage, people are replacing their conventional light sources with LEDs. And voltage range also 1 to 2 volts, it's a small one. And current also required just 5 to 20 milliamps. The total power output will be less than 150 milliwatt. The response time is very less, and it's only about just 10 nanoseconds. The device does not need any heating or warm-up time like conventional light sources like a sodium lamp or mercury lamp. And the size is very small because of its miniature size. Even in screens also we are able to use LEDs. Have a rugged construction, and hence it can withstand for shock and physical shock and vibrations. And LED has a very good lifespan. It's around more than 20 years. Now, but coin has the other end. There are disadvantages with LEDs also. A slight excess in voltage or current can damage the device. So while connecting, better to connect using a resistor to reduce the damage. And this device is known to have much wider bandwidth compared to laser. The temperature dependent on radiant output power and wavelength. Now we see the applications of these LEDs. So LEDs are used in bulbs at homes and industries, and light emitting diodes are used in motorcycles and cars for designing or brake lights. At traffic signals, LEDs are used. These are used in mobile phones for indication and also for flashlight beside camera in the mobiles. So in simple, LEDs can be used at any place. Now, based on this topic, we can do some problems on this one. If the energy gap in LED is 1.960 electron volts, then what's its wavelength of LED? Already we had discussed in a concept that energy gap, based on energy gap, wavelength will be there. Now, you can write the given data and lambda, the wavelength is hc by Eg. We know h is a Planck's constant, c is the velocity of light. Now before solving, we should convert the joules into electron volts for the Planck's constant. And then by solving, we will get this one answer as 632.65 nanometer, or you can say it's 6326 angstroms. You can represent in any units. And the output color is red color. Similarly, we can see one more a similar problem. This one, very much similar, only I changed the energy gap, then wavelength is going to be changed drastically in this case, and here 867 is in not in visible region, it's infrared. Generally these LEDs are used in TV remotes. If LED is emitting a wavelength of 5800, then what is energy gap of a diode? The same formula is used. So if you solve, you are going to get 2.13 electron volts. So like this, we can solve problems based on LEDs. So link for write-up or notes of this topic as given in the description. You can go through it. Happy learning. Like, share, comment, and please subscribe my channel Physics Medicine. Please post your questions below, or if you have any tough topics, please post it in comment box. I'll try to give a video on that. For more updates, subscribe my channel. Thank you very much for watching. Thank you.